Section 6 goes over logic again. We're going to go into biconditionals, which is just another form of a conditional statement. We'll go over what that means, and we're going to see an example of how to do a proof, either in the paragraph form or the two-column proof. And remember, we're going to do the two-column proof more often than a paragraph form. And all of these, of course, still stem from deductive reasoning, where we are taking rules and creating facts from them. So let's go on with biconditionals. A biconditional is basically just saying both directions for this statement must be true. The symbol for a biconditional is a double-headed arrow. You can see that arrow kind of goes in both directions. And you would pronounce it when you see that as if and only if. You can write that as the word if with two F's. You would pronounce this as if and only if. So when you see it written in logical form like this, P, and then the double-sided arrow, and then a Q, what it means is both if P then Q, and at the same time, if Q then P. Now notice this is an and, not an or. It's a conjunction, not a disjunction. Both of these must be true for it to be considered a biconditional. Again, the biconditional is only true when both conditions are true statements. So we're going to write the pair of conditional statements as a biconditional. This is just kind of an example. You can kind of see how this works. If P is a prime number, then it has exactly two factors. So think of a prime number like 5. 5 has only two factors, 5 and 1. So that's a true statement to say if P is a prime number, then it only has two factors. Also, let's think of if P has exactly two factors, then it is a prime number. Well, again, that's just kind of the definition. Of course, if it has exactly two factors, then it's going to be a prime number. But notice that one is if P then Q, one is if Q then P. So that it's the same thing, but kind of split. Kind of looks like this. It has to go in both directions. So we're going to rewrite it as a biconditional statement. P is a prime number if and only if it has exactly two factors. Now this red version, this is all you need. You can just say it this way. In this form, I put the prime number part first. In this form, I put the exactly two factors part first. P has exactly two factors if and only if P is a prime number. Now notice, this form I used that three-letter if. This form I actually spelled out, if and only if, together. Okay, so if and only if, and this three-letter if, they mean the same exact thing. Actually, that's how you pronounce this, if and only if. This one I put prime number first, this one I put two factors, but technically these are saying the exact same thing. For another example, we're going to rewrite using the if and only if form. A quadrilateral is a polygon with four sides. Again, notice we're using a definition. The definition of quadrilateral is a polygon with four sides. That's how we know for sure that it's going to be true statement either way we put it. So we can use if and only if. A polygon is a quadrilateral if and only if it has four sides. A polygon has four sides if and only if it is a quadrilateral. Again, you don't need to write both of these. I'm just showing you that there are two possible ways to do it. One where you start with quadrilateral, one where you start with the four sides, one using if and only if, one using the three-letter if. Either way works. For another example, we're going to look at the pair of given premises are true. So then what's a valid conclusion that you can draw? So in this case, they are giving us a biconditional. It says 258 is divisible by 6 if and only if 2 and 3 are both factors of 258. They also told us that 2 and 3 are both factors of 258. So what I'm going to do is actually cross this out just for now. You don't need to cross it out. I'm just going to block it out. And we're going to say, let's pretend the only information we knew was this biconditional, and we knew that it was in fact true. Taking that biconditional, which I rewrote in green here, we can split it up into two separate statements, two separate conditional statements. One of them says if 258 is divisible by 6, then 2 and 3 are both factors of 258. Okay? According to this statement, because it is biconditional and it goes both ways, this is a true statement. This is also a true statement. If 2 and 3 are both factors of 258, then 258 is divisible by 6. Both of these are true statements that we got from this. We basically just broke this down into two true things. Now I'm going to go back and put this fact back in there. We know for sure that 2 and 3 are both factors of 258, saying this is true. Well, if this is true, what does the red sentence tell us? Well, technically the red sentence doesn't really tell us anything, because the hypothesis is if 256 is divisible by 6. And this fact didn't tell us anything about divisible by 6. So technically the red one gives us no conclusion. But if we look at the blue form, the blue form says if 2 and 3 are both factors of 258, so this statement shows that this is a true hypothesis. And if this is a true hypothesis, then the conclusion must be true. So, if 2 and 3 are both factors of 258, then 258 is divisible by 6. So what valid conclusion can we draw? Well, we can say that 258 is for sure going to be divisible by 6. That is our valid conclusion drawn by this biconditional and this fact. Let's look at an example of a proof. We're going to look at it both as a paragraph proof and then a two-column proof. First, we'll do it as a paragraph proof. Now the question says, we are given the fact that Q is the midpoint of PR. So here's Q and here's P and R. Now I know it doesn't look like the midpoint, but because they told us up here, we can assume that, oh yeah, for sure that's going to be the midpoint. We also know, because we are given, that R is the midpoint of QS. Now again, it doesn't necessarily look like it's the midpoint, but they told us for sure that it is. Our job is to prove that PQ is equivalent to SR, meaning this distance is the same as this distance. So, in a paragraph form, we would have to say that since Q is the midpoint of PR, then PQ is congruent to QR by the definition of a midpoint. And if we wanted to draw that in, we could say PR is the same as QR. These are congruent lengths because that's what a midpoint means. Similarly, since R is the midpoint of QS, then QR is congruent to RS. I'm going to use a different tick mark. I'm going to use double, and I'm going to make them blue. So, we figured out if R is the midpoint, then by definition, this is the same as this. If Q is a midpoint, this is the same as this. Now notice, this piece has both tick marks on it, meaning we technically shouldn't put different tick marks on there. We need to, where's my eraser? We need to keep them all the same tick mark, just the one red one. This is the same as this. This is the same as this. Thus, we can see on our drawing, using the transitive property, PQ is going to be congruent to QR. QR is congruent to RS. Thus, PQ is congruent to SR by the transitive property. This equals this. This equals this. So, this one equals this. So that would be a paragraph form of a proof. Now, we can do the same sort of proof in a two-column form. Again, we will just start with whatever we were given. So, step 1, Q is the midpoint of PR, R is the midpoint of QS. That was given. Now we can say that PQ equals QR and QR equals SR. How can we say that? Well, that's just the definition of a midpoint. So, looking at all of these equivalent signs here, we can transfer PQ all the way to SR. So PQ is the same as SR. How do we know that? Well, it was the transitive property that we used from this step 2. We had to use this step and the transitive property together to get there. So again, similar to it, this is basically deductive reasoning. We took this rule, we took this rule, and we made a new fact. So we were able to prove, as they asked us right here, that PQ equals SR. And that'll cover it for our very first unit.